Right now, somewhere, a chatbot is halfway through a sentence, and it has no idea how that sentence ends. Not vaguely, not sort of, it genuinely does not know. There's no draft sitting in memory, no plan, no outline. It's choosing one word, then forgetting the future entirely, then choosing the next one. That sounds insane for something that can write essays, fix your code, and explain quantum physics. So today we're opening the hood. No hand waving, no, it's just magic. The actual pipeline, from your keystroke to its reply. There are 5 stages. Let's go one at a time. First problem. Computers don't do words. They do numbers. So before anything clever happens, your sentence gets cut into chunks called tokens. Type unbelievably into a tokenizer and watch it split into 3 or 4 fragments instead of staying whole. Type cat and it usually survives as one piece. The rule isn't grammar, it's frequency. Whatever chunks show up constantly in training text get their own single token. Rare or complex words get sliced into smaller, reusable fragments. This is decided before the model ever runs. It's a fixed lookup table built in advance, not a judgment call the network makes live. Here's the part that trips people up. When a company says 128K token context window, that is not 128,000 words. Depending on the language, it's often closer to 90,000 to 100,000 words, sometimes less. Punctuation, spacing, even capitalization can quietly cost you tokens. Once your text is chopped up, each fragment gets swapped for an ID number. Your whole message becomes a plain list of integers. That list is the only thing that enters the model, not your sentence, just numbers. An ID number like 4,721 tells the model nothing on its own. It's a label, not a meaning. So the next step converts every token into a long list of numbers called an embedding, sometimes thousands of values long. Think of it as a coordinate. Every token gets dropped somewhere in an enormous invisible map, and the position is what encodes meaning. Words used in similar situations end up parked near each other. Doctor and physician land close together. Doctor and bicycle land far apart. And this map captures relationships, not just similarity. There's a well-known example where taking the coordinate for king, removing man, and adding woman lands you almost exactly on queen. Nobody programmed that rule. It fell out of patterns in the training data. This is also why a model can tell that Java the programming language and Java the island are almost unrelated, even though they share a token. Their surrounding context pulls them to completely different regions of the map. At this point, every token is a rich, meaning-loaded vector. Now they need to talk to each other. This is the transformer, the architecture behind basically every major model today, and the single idea worth understanding is attention. Picture a room full of translators, and every word in your sentence gets to ask the others, how relevant are you to me? Take the sentence, the trophy didn't fit in the suitcase because it was too big. What was too big, the trophy or the suitcase? You know instantly. The model has to compute it. Through attention, the token it ends up strongly linked to trophy and weakly linked to suitcase, purely because of patterns absorbed from enormous amounts of text where that kind of sentence structure appeared before. This isn't one lookup. It happens in parallel across dozens of attention heads, each one tracking a different kind of relationship. Grammar, tone, cause and effect, who's speaking. Then the entire process stacks, layer after layer, sometimes 80, 90, or more, each one sharpening the model's read on the sentence a little further. By the end, you don't have words anymore. You have a deeply contextualized signal, ready to make a prediction. Here's the moment that changes how you should think about AI forever. The model doesn't produce an answer. It produces odds. For every single token in its vocabulary, often well over 100,000 candidates, it assigns a raw score. Those scores get run through a function called softmax, which converts them into a clean probability distribution that adds up to 100%. So if the sentence so far is, the capital of France is, the model isn't thinking Paris. It's calculating something like Paris, 71%, the, 8%, a, 4%, located, 3%, and 100,000 plus other options splitting up whatever's left. That's it. That's the entire intelligence moment. A giant, context-shaped guess about what token comes next. Nothing more, nothing less. So who resolves the bet? A sample.
A sampling method. And this is the one part of the whole pipeline you can actually control. The laziest option is greedy decoding. Always take the single highest scoring token. It's reliable, but often flat and repetitive. More interesting is temperature. Turn it down and the model plays it safe, leaning hard into the top candidates. Turn it up, and lower probability tokens get a real shot. Output gets more varied, more surprising, and past a certain point, more likely to go off the rails entirely. There's also top P sampling, sometimes called nucleus sampling. Instead of picking from the entire vocabulary, the model narrows the field to the smallest group of tokens whose combined probability hits some threshold, say 90%, and only samples from that shortlist. Rough guide if you're calling an API yourself. Coding and factual tasks, keep temperature low, around 0.2 to 0.3. General assistant behavior, around 0.7. Brainstorming or creative writing, push it toward 1.0 or above. Once a token is chosen, one single token, the process isn't done. It's barely started. Here's the twist. The model doesn't write your whole reply and then show it to you. It writes one token, glues it onto the end of everything so far, and restarts the entire 5-step process from scratch. Tokenize, embed, attend, predict, sample to get the next token. Ask, what's the tallest mountain? And the first pass might produce the. Now the input is, what's the tallest mountain? The. Second pass produces tallest. Third pass, working off an even longer input, produces mountain. And on, until it hits a stop signal or a length limit. This is also why long responses get slower. Every new token means reattending to a longer and longer history. And it's why there's no hidden script sitting in the model's head. Token 40 genuinely doesn't exist yet when the model is generating token 5. It's decided completely fresh, every single step, based only on what's been written so far. 3 takeaways worth keeping. 1. Hallucinations aren't the model lying. There's no intent there at all. It's producing whatever sequence statistically resembles a confident answer. Confidence and correctness are 2 completely different signals. Verify anything that matters. 2. Temperature doesn't make a model more creative in any human sense. It makes unlikely tokens statistically eligible. What feels like creativity is you, the reader, interpreting randomness as intent. Useful to know when you're tuning an API call. 3. Context window limits aren't a company being cheap. Attention scales expensively. The cost of relating every token to every other token grows fast as the input grows. The wall you're hitting is math, not policy. So next time you send a prompt, you'll know what's actually happening underneath. Your words getting chopped into fragments, turned into coordinates in a meaning space, filtered through layers of attention, collapsed into odds, and picked one gamble at a time, over and over until it stops. It's not thinking the way you think, but understanding the mechanism is what lets you actually use it well. If this made things click, drop a like and share it with someone still convinced their chatbot is planning ahead.